my Python skills mainly through this website, or it's a competition. I don't know what you want to call it. It's called Advent of Code. And it started on the 1st of December. As you can see, I haven't entered the competition this year. I haven't even looked at what the challenges are. But you get a series of problems every day. It's actually 2 problems every day that you can solve. And then, once you solve one problem, the next problem is unlocked. So I found these problems to be much more useful to work on. They develop my learning a lot more than some of these other websites that are out there. So I highly recommend this. It's not limited to Python. So if you want to solve these problems using MATLAB or C or C++ or Java, that's perfectly fine. I know last year when I was actively doing this, there was somebody who solved everything using Excel macros. I have no idea why, but hey, it's completely up to you, right? As you can see, the website is extremely bare bones. It's just the focus is just on the competition itself. There is also a Reddit and people post their solutions. So what I used to do is, solve the problems on my own, submit the answers, and then I would go and look at how other people have solved it. And that's what helped me uncover areas of Python and ways of doing things that I hadn't even thought of, right? So it's the same thing with when I recommend looking at some of these data sets and notebooks associated with them. We will approach problems in a certain way, conditioned by the way we've been trained or the way we've been used to doing things. Looking at how other people do it can offer a very different perspective on the possibilities and open up new arenas for us to explore, right? So that's what I wanted to say about this. Okay, so now let's look at the application that I wanted to talk about. And as you can see, this is called ECG classification. If you go to Kaggle and search for ECG classification, it's one of these. I'm not sure which one. These are notebooks. So let's just search for ECG classification and data sets. And there you go. You get this heartbeat categorization data set. And you can go in, or this is all free of cost, right? So there's no payment associated with this. And there's 2 different data sets out here. One is from MIT, the other is the PTB Diagnostic ECG database. I think that's the one that I'm using. You can download both of them. You can explore them and see what, how you could want to use them, right? So the one that I'm using is this PTB Diagnostic categorization dataset. I have a link in this notebook. The notebook will be shared with you. But let's look at the Python part of it. The environment that I'm using is what's called a Jupyter notebook. And I think it's very familiar to a MATLAB notebook. Although with MATLAB, I haven't worked with notebooks before, so I can't make that statement. If you're doing anything in Python, there's 3 libraries that I highly recommend you get very familiar with. The first is NumPy, which stands for Numerical Python. And this is the part where, one of the questions, not one of the questions, we've just had one question thus far. But the question was about Python being slower than MATLAB. And it's libraries like NumPy that help us overcome that. So it does, even if you write like something that's in a for loop, it actually compiles, they have compiled code implementations. So that's written in C, and it's just a Python interface. The second library that you should get very familiar with is matplotlib. And just from the name itself, you can guess where what the interface is going to look like, right? It is directly inspired by how MATLAB does its plotting, hence the name. And you'll see examples of this in the rest of this notebook. The third library is something called pandas, which is a short form for panel data, right? So if you have data in a table, and we'll see some of that as we go ahead, pandas is the library to use. I typically, and this is standard, I alias NumPy as NP, pandas as PD, And I don't use matplotlib directly. I use a sublibrary called pyplot, and I alias that as PLT. The second, for the purposes of this talk specifically, the second library that I would highly recommend is this thing called sklearn or scikit-learn. If you were to just Google this, you'll see the website for scikit-learn, and you should feel free to go and explore and look at all of the models that are available out here, right? So you have separate implementations for classification algorithms, regression, clustering, dimensionality reduction, model selection, pre-processing, and result presentation as well, right? So feel free to jump into each one of these, play around with them, get a feel for what's where. What I will be highlighting is the library design itself is pretty fantastic. So any model that you want to use involves a very simple interface, which I'm going to talk about, right? You instantiate a model, you train it, and you evaluate it. So if you keep these three in mind, and the interface is same for different models, you're well on your way to using scikit-learn. Okay, so I'm importing a bunch of libraries from sklearn. Don't worry about these. We'll talk about it as we go ahead. What we're going to be playing around with today is the heartbeat categorization data set. This is a link to the same thing. What I wanted to point out here is that you have two databases in this. The one that I'm using is this PTB diagnostic database. This one has it's classified into 5 classes. The PTB diagnostic is just classified into 2 classes, right? And I think the names of the 2 files are also normal and abnormal. There we go. Abnormal and normal. That's just the name of the file, right? It's a CSV file, comma separated values. So let's explore those a little bit and see what exactly these do. So the first, I guess I should probably run these imports. Okay. The first thing I'm going to do, and this is where, I'm just going to jump in and talk about Python and the libraries, and I'm not going to worry too much about talking about the details. But I think with a reasonable amount of MATLAB or other programming background, this should be fairly easy to understand. So the first thing I'm doing is I'm reading this CSV file using a function called read CSV. And because these are in separate files, I'm reading them into what's called a data frame. So Pandas works in terms of what are called data frames, and they are read into 2 data frames, one called DFN and the other one called DFA. Okay. What I'm going to do is I'm just going to say, okay, a couple of things that I'm going to recommend when you're using Python. This is one function that I use a huge amount of. If I just say type of DFN, it'll tell me what the type of that particular variable is. So this is a data frame. Okay. If I want to find out, okay, by the way, so everything in Python is an object, right? And don't worry if that doesn't mean anything to you. If it does mean something to you, you'll recognize that an object is something that has attributes and classes. So you could say, okay, what kinds of things does a data frame have? So I can just type dir df, and it gives me a whole bunch of different attributes of a data frame object. So I can say df.add, for example, or add prefix, add suffix, and so on. And we are going to be doing some of these. You'll also see that there are, right at the beginning, there are these special attributes that begin and end with a double underscore. So these are called dunder variables or dunder attributes. You're not supposed to use them directly unless you're actually writing your own classes. So ignore those, focus on the ones that come later. And you might get ideas about the kinds of things that you can do with a data frame. Okay, but let's not worry about that. Let's look at what exactly have we read in. So if I type head 5, it's going to show me the first 5 rows that it's read. And when I look at this, I see something interesting. So These are the 5 rows. It's added this index 0, 1, 2, 3, 4. The values, it says it has 188 columns. So I can go all the way to the end. That's the last column. And it looks like there's a bunch of values out here, right? 1.793511.17. But the column headings are something that are really weird, right? And then, okay, so you say, okay, what the heck is going on? Why would somebody label this column as 1 or label this column as 0.90032? Then you realize that, okay, this is also data, right? So when you see something like that, you say, okay, how do I tell read CSV that the first row is also data? It's not the column headings. You do that by giving giving the read CSV option that says header is equal to none. And you'll find this throughout the code that I'm going to show you. You can customize a lot of these functions, a lot of these objects, a lot of these algorithms by using a different set of options. Okay. I just wanted to show you this. If I say what's the shape, it's got 10,505 rows and 188 columns. This is for the abnormal data. If I say N, the normal data has 4,045 rows, 188 columns. But this is ignoring the first row, which it's interpreting as a header. So let's just run this. And then when I say, what's the head? This looks a lot better. 1.9, 0.35, 0.05. And the column headings are 0, 1, 2, 3, all the way to 187. Zero-based indexing, therefore 188 columns. It's got 10,000 rows. If I print the shape now, it goes 10,506 and 4,046. If you remember before, this was saying 4,045 because it was ignoring the first row. Okay. Now, if we look at this, this data is kind of difficult to parse. I mean, how do I make sense of this, right? And I don't know about you, but for me, I'm a very visual person. So it's a lot easier to understand what's going on with data if we can visualize it, right? And you remember I said Matplotlib is a direct derivative of MATLAB. Imitation is the best form of flattery. So I can just go ahead and say, okay, print me the data that's at location at row number 500. Just plot that for me, right? So all I have to do is a single command. And this goes ahead and gives me a plot that looks like this. Now, I'm not from the biomedicine background. I did a little bit of reading before making these slides. And then it turns out that each of these, so this is what a typical heartbeat looks like. I'm not sure if that spike should be here or whatever, but then you have all of these labels for, I think it's PQRS or something like that. So, or NO, or I don't know. So you have these different phases of a heartbeat. And this is actually one heartbeat but it's the readings from all of the sensors, but more importantly, the x-axis goes from 0 to 188. So it's taking each value and it's plotting its value for each index. So great. So, this is one. Suppose I wanted to view a few of these and I wanted to say, okay, how does the abnormal data compare to the normal data? Fairly easy to do in Python. So I'm going to create a grid of 2 rows and 5 columns. And in the first row, I'm going to plot normal data. In the second row, I'm going to plot abnormal data, right? And I've just randomly generated indices out here based on where we are in the loop. So if I run this, I can easily generate this grid, right? Where these are normal data heartbeats. These are abnormal heartbeats, right? And maybe this means something to you and you can look at these and say, oh yeah, that's not right, but I'm not a doctor. So, well, at least I'm not a medical doctor. So I can't claim any expertise on that, but it's good to visualize this, right? It's good to see how things are going. Okay, I'm going to take a quick pause out here and just ask everyone, is this pace too fast or too slow? Do you want me to go into more detail or should I hurry things up? What's, just post things, post your response in the chat window. So I'll know I'll know how to adjust or if you're going this in the right place. Okay. Now what we're going to do is we're going to try to build a model that goes ahead and tries to understand this data, and we are going to try to build a model that's going to predict if we have unknown data, whether it is normal or abnormal. Okay, so the first thing that we need to do is we want to combine, this normal abnormal data into one data set, right? So in order to do that, I want to add a column to these 188 columns that already exist. So I'll just responding to a comment out here. I will share the code right after this, right? So just bear with me while we're going through it. So what we're going to do, so adding a column is very straightforward. We just say df square bracket n is equal to whatever value I want to. In this case, I'm adding a column called n, and if in the data frame for normal, I'm giving it a value of 1. In the data frame for abnormal, I'm giving it a value of 0. So if I do this and look at the first 3 rows, you'll see I have the previous 187 columns. Then I have a new column called n, which has values of 1 because I said dfn. If I look at the abnormal data, it's the same thing, but the normal column has values of 0. Okay, so why do this? Hey, great. Now, if you look at the data, we've got now 189 columns. Why are we doing this? So that I can combine these 2 data frames into a single data frame. How do I do that? I just concatenate them. Right? So great. If I do this and I look at the shape, 4,000 plus 10,000, I get 14,552, right? But the number of columns is of course still 189. So it's just kind of put one data frame on top of the other. But if I print the data frame, I see something interesting. What I see is the rows go from 0 up to 10,505. The columns go from 6, 7, 8 all the way to 185, 186, 187 up to n. But the rows are going from 0 to 10,505. Also, so it looks like only the abnormal data has been used, but the first rows have a n column of 1, the last have 0, and it still says that there's 14,552 rows. Right? So what's happened essentially is when it concatenated this, it also concatenated the indices. So this 0, 1, 2, 3, 4 are the indices in the normal table. The 10,501 to 505 are the indices in the abnormal table. Right? So again, as before, I just add a flag out there that says ignore index. Right? And now if I run this, I have again 14,452. And the rows go from index number 0 to 14,451. So it always had 14,452 rows. It was just indexed according to the original data. Okay. So why did we do this? Now what we want to do is we want to extract a random set of rows from here to build our model. And we want a different set so that we can test our model. Okay. So the way we are going to do this is using a helper function called train test split. Okay, so let's just look at, and by the way, so a lot of these options that you see inside out here are optional. In fact, what I've used is the default values, but I'll tell you why I wanted to explicitly put them out here so that you guys get exposed to it and you're familiar with it. Okay, so what are the options out here, right? What exactly is this function doing? So the first thing is I'm saying shuffle is equal to true. So it's going to randomly sample from these 14,552 rows. We obviously want that because the first 4,000 are normal, the last 10,000 are abnormal, and you don't want to take just some of them. Okay. Random state is equal to 2 is just so that I seed the random number generator so that I can repeat this as needed. This is where things get interesting. I'm saying test size is equal to 0.2. It's a fraction. So basically, I'm saying that split this data into a training set and a test set. The training set, I want to be 80% of the data. The test set, I want to be 20% of the data. So I'm going to build a model. I'm going to train a model based on the training set. I'm going to evaluate the model based on the test set. And now you can see why I want shuffle equal to true, because I want to randomly have like a few tests to be normal, a few to be abnormal. And I want to check whether the prediction is correct or not. Okay. What is the data that I want to split? This is the most important part. So I wanted to take data frame in which locations, all the rows, but only the first 188 columns. This is going to be my data, right? The labels are going to be in the last column, df.m, right? What is it going to return? It's going to return four things. It's going to return the 80% of this table in the train data, 20% in test data. Corresponding to the train data, I'm going to get the training labels in this array and the test labels in the test labels array, right? So again, that's a lot of functionality that's available using just this particular function. And then let's run this. And then I could say, okay, let's just check to see what we have, right? So lo and behold, the train data is 11,000 by 188. The train labels is just 11,641, as you would expect. And then 2,900 test data and 188 columns for the actual data. The labels are just single values, so you don't have any columns out there. Okay. Now, the first model that we're going to try to build is a K nearest neighbor classifier. Are you guys familiar with a KNN classifier? So if so, just put a message in the chat box. I'm going to assume that you are. So I'm not going to spend too much time on it. What I did want to also point out, so we've already seen the function dir and type. Here's another very useful function. So if you just give any object and you say question mark, it gives you the documentation for that particular function or object and what all parameters are there, and then sample values and examples of how to use it, right? So if you don't want to go and look it up in a website, it's available for you out here itself. Okay, what am I going to do out here? I'm just now remember what I said, that scikit-learn has a very straightforward interface where you create an object, you train the model, and you do a prediction. So out here, we are just creating a model. This n.fit is doing the training. So it's fitting the data to the model. What is the data? This is the data, and these are the classes that it belongs to, either 0 or 1, right? And then I'm going to say n.predict on the test data, right? And P is going to hold the predictions for each of those 2,900 entries that we had. So if I run this really quickly, I'll talk about some of these parameters in a second. Okay, so basically out here, the main thing I want to point out is this n neighbors is equal to 5. So in a k nearest neighbor, it's going to look for 5 closest points, and then it's going to choose the maximum among those as the label for this particular prediction. Okay, so if I say, okay, what is this P? Sorry. It's a vector of 2,900 entries, and it's got a mixture of zeros and ones. Those are the predictions, right? The test labels are also zeros and ones. So there's multiple ways I can evaluate how well this has done. I could either say, just do P minus test label. So this will do a vector subtraction, store it in diffs. I could say diffs is also 2,900, right? And then I can call a helper function in diffs called value count. So what value counts will do is it'll look at the unique values inside diffs, and it'll tell us how many instances of those there are. So for example, out here, my predictions are ones and zeros. My test labels are ones and zeros. So diffs can either be, so if the prediction is correct, right? A 1 is predicted as a 1, a 0 is predicted as a 0. their difference is going to be 0. But if I have a prediction of 1 and a test and a actual value of 0, I'm going to get a diff of 1. Or if I have a prediction of 0 and a test label of 1, the value is going to be -1. So if I print this diff's value count, right, here's what happens. Out of those 2,911, 2,908 were correct. 2 of them show a -1. What that means was our k nearest neighbor classifier predicted that this was a 0, but it was actually a 1. So 0 minus 1 gives us a -1. And similarly, it predicted a 1 when it was actually a 0 one time. So this is pretty freaking awesome data, right? Out of 2,911, it's given only 3 wrong answers. Everything else is correct, right? There's a couple of very useful helper functions that scikit-learn provides. I could say, what's the accuracy score? It's 99.89%, right? I could also ask for the confusion matrix, which says, okay, a 0 is predicted as a 0 2,084 times. A 1 was predicted as a 1 824 times, and then 2 and 1, which are the same as these two, right? Okay, now, so this was kind of the basic setup of pretty much everything we can do with sklearn. Create a model, fit the data, or train your model, and predict the values. So now I could say, okay, I took a default of 5 nearest neighbors. What if I vary it between 1 and 15? I can do something like this. Now, this is Python syntax, but I think if you see this, you'll see how easy it is to understand. I'm saying for n in 1, 2, 5, 10, and 15, create a classifier of with n neighbors equal to n, call fit, call predict, and print the accuracy. So if I run this, and it'll take a couple of minutes to run. You can see that n neighbors of 1 is actually better than even, or 2 is even better than 5 that we had before, right? But anyway, I wanted to use this more as an example of how you build and train a model. So don't worry too much about the accuracy. Okay. The other thing that I was thinking of doing was, I said that, instead of using the entire 10,000 or 11,000 training set, what would happen if we had fewer elements in there, right? So I said, okay, let's split this entire space. And I think linspace is something I've seen in MATLAB as well. Let's split this from 0.1 to 1 into 10 groups, right? And then the same loop as before, but instead of fitting the data on the entire training data, I do it on the first 10%, 20%, 30%, 40%, right? And what you would expect is if I'm using only 10% of the data, my accuracy is lower and it increases as we increase the amount of data. So if we run this, I need to do this first, sorry. When I run this, you'll see with taking just 1100 samples, 98.3, but even at 2000, we are at 99.03, 99.3, and it increases as we go towards 10. Okay, so that's that. The third experiment that I wanted to show you, and this is actually something pretty cool, is dimensionality reduction, which again, I'm going to assume that you guys are familiar with and are aware of. So what I'm going to do out here is kind of go backwards. I'm going to make a copy of this data frame, right? I'm sorry. I'm first going to copy the labels in that data frame, and then I'm going to drop that column from data frame, right? So now if we look at this, it'll run after this is completed. Anyway, so by the way, this you can see the runtime increasing because it's looking for oh, this is just increasing. Sorry, I thought I was confusing it with, with n equal to 15, the runtime is much higher because you're looking for 15 nearest neighbors, but not by much. Anyway, so Now what I'm going to do is I'm just going to call, I'm going to instantiate a PCA model. PCA stands for Principal Component Analysis. So all I'm going to do is I'm going to instantiate the model. I'm going to, okay, there's the head, but that's okay. I'm going to call fit. And then instead of predict, I'm going to call transform, right? So D is the model. DF is the data that we have, the data frame that we have, right? And I'm going to store that in a data frame called reduced. So if I run this, this option that I've given it, the 15, those are the dimensions that we want. Remember, the original data, I didn't say this explicitly, but I'm sure you guys are comfortable when I say that the original data has 188 dimensions. So even when we were doing the nearest neighbor approach, the nearest neighbor computations, we were essentially doing Euclidean distance in 188 dimensional space. So out here, what we end up doing is we are reducing that 188 down to 15. Is 15 enough? We'll see. But if you look at some of this, the right hand side of the data, there seem to be a lot of zeros. So there definitely seems to be the possibility of reducing a lot of these dimensions, right? But how well did we do, right? So first of all, okay, let's make sure. We started out with 14,552 rows. We have 14,552 rows. We're not changing that. But we started out with 188 dimensions and it's down to 15 dimensions, which is what we wanted it to do. Great. How much of the variance is captured by these 15 dimensions? So I can print the explained variance ratio that will print for each dimension what was the variance that it captured. And if I add all of it up, it'll tell me what the total variance is that I've captured. So for example, out here, these 15 are the first 15 dimensions. The first one captures 37.6% of the variation, 12.5, and then it drops off 6%, 4%, 3%, 2%, and so on. If I add all of these up, these 15 dimensions is capturing 82% of the original variance that the 188 dimensions had. I could also do the same thing for 5 dimensions. And of course, out here now the columns are reduced to 5. And then if I run this, of course, these 5 are not going to change, right? But instead of 82%, now we have about 65% of the variance explained. So it's up to us to figure out, how comfortable we are with this. I mean, we could go all the way down to 1 dimension, but that would just capture about a third of the total variance. Okay. Now let's try to visualize this, right? Now, the only reason why I did this because the visualization doesn't give us any real insight, but I wanted to do this so that you could see how easy it is to do these kinds of plots. So basically what I'm going to do is I'm going to take df.reduce and I'm going to plot column 0 versus column 1 as a scatter plot. So straightforward enough, I'm saying plt.scatter, use this value as x, use this as y. And then I'm going to say, use the labels to color it. What are the labels? These were basically the zeros and the ones that I had created a copy of right at the beginning, right? And I'm also saying if it's a 0, then color it gray. If it's a 1, color it green, right? The alpha is just giving me a transparency factor. So it makes the figure a bit easier to look at, right? Now remember, this is the 0th dimension and the first dimension, right? The grays are abnormal and the greens are the normal data. This looks a bit noisy and it's kind of difficult to figure out what's going on out here. So I can do the same thing as I did before and create a 1/2 grid. In the first one, I'll just plot the so the 4046 are all the normal data, and after 4046 is the abnormal data. So I'm plotting the normal and abnormal separately, right? And there you go. So this is the normal data. This is the abnormal data. We could kind of put on our human hat and look for patterns where none exist, and say that, oh, there's this V-shaped curve for all of the data, and then there's this structure out here, there's this clump out here, but honestly speaking, that's just fooling ourselves. It's just data, and that's fine. Now, if we just look at the first two dimensions, they account for about 50% of the variance. What we're actually going to be doing is, I think I'd set the number of dimensions to 5. So if we now try to do a model using this, it's going to be a 5-dimensional model. It's going to be calculating distances in 5 dimensions, right? What do we do out here? We create train and a test data. You can look at the shape and it's going to be the same as before, except now these guys have only 5 dimensions instead of the 188 that we had before. I'm going to create a k nearest neighbor classifier. I'm going to call predict, and I can do the same thing as before. I can look at the value counts, and now you'll see we had 2 and 1 before. Now we have 11 and 11. So it's significantly worse, but hey, in 2900, if we just have 22 misclassified values, I think that's brilliant, right? The accuracy is 99.24. Okay, so I tried it for 5, right? But then maybe I say that, okay, let's do this for many more, right? Similar to the way we experimented with k nearest neighbors, where we varied the number of neighbors from 1 through 15 or something like that. I can do the same thing. I could say reduce those 188 dimensions to 128, 64, 32, 16, 842, right? In each case, I'm saying create the model, call fit, transform the data, right? Then split the data, create a k nearest neighbor classifier, train it and call prediction, and show me what the results look like, right? So if I run this, you'll see immediately, give it a second to run. The accuracy, so with 128, we are capturing 99.81% of the variance. And as the number of dimensions goes down, the variance goes down. Accuracy isn't that, I mean, for this problem, it's not really affected too much by, in fact, it seems to get better as we go to lower values. So this is just noise, by the way, don't read too much into it. But for 2, you're capturing only 50% of the explained variance, and your accuracy does really go down to 74.6%, right? So this is kind of, I like I said, my goal was just to give you a very high level overview of how we take a particular problem from biomedical engineering and say that, okay, can we just do a very simple classifier on this, in this case, a k nearest neighbor. But then we also said, okay, how do we vary different parameters, right? How do we then do something like a principal component analysis? And as you can see, there's very little amount of code. Well, it's little amount of code because I know how to use them. But even otherwise, even if you're experimenting with it and playing with it, it's not too difficult to do a lot of things with a reasonably small amount of code. Okay. Now let's do something. Let's see if this approach applies to other kinds of models as well. And then we'll also look at a new kind of approach to doing the for loops that we looked at. So what I'm first going to be looking at is I'm going to create a naive-based model. And because my classes are just 0 and 1, I'm happy with a Bernoulli distribution, right? So this is a Bernoulli naive base. It's got 2 parameters, binarize and alpha, and don't worry about what these mean. But what I'm doing is I'm going through different values of binarize. What am I doing? I'm creating the model, I'm training it, and I'm calling predict, and I'm printing the accuracy. So this is the interface to scikit-learn that I really want you guys to take away. Like if there's nothing else that you get from this, get this. For the scikit-learn library, create the model, train it, and use it. Right? Those are basically the 3 steps. If you're using PCA, using it means calling the function transform. If you're using a regressor or a classifier, it means calling the predict function. That's basically all that there is to it. And this applies to pretty much all of these models that you see in each one of these, right? Instantiate it, fit, and predict. Okay, so out here, and I'll quickly tell you what the binary, oh, I ran it already. Okay, so what binarize does is it looks at these values, right? The 0.11, 0.34, 0.07, and it uses this to also map that onto a 0-1 space, right? Then it builds like a covariance based model, and then you can call predict based on it, right? Alpha is a linearization parameter, and I think there we go. So out here I'm varying alpha, right? And then again, create the model, fit, predict, and train it. And if I run this, I get different values of alpha, I get different values of accuracy. Okay. Now, the thing is, okay, what if I want to do both? Then I could put this in a double for loop and then say, okay, let's do this. Or I could say, you know what, let's see out here. My best alpha is, it's actually alpha is not making any difference at all, right? Out here, 7193 seems to be the best, and then use whatever alpha. But then what I wanted to show you is this thing called grid search, right? Out here, what I do is I'm going to say create a grid search object called fit, and then I'll show you how to, well, the fit actually runs it as well. But here's what I'm giving it, right? I'm saying take this Bernoulli knife-based model, BNB, that I've created, right? And I'm giving it, this is what's called a dictionary in Python. So the key is alpha, and the values it can take are this. The key is binarize, like you see out here, and these are the values it can take. And why is it called grid search? It's going to take the cross product of these values. It's going to instantiate this guy, and it's going to figure out which one gives us the best results. I'm not going to go into the details of cross validation, but essentially it's going to take the 10,000 or 11,000 training set we have, divide it up into 5 sets, and it's going to apply this for each one of those. So it's going to have like 1 set or 4 sets for training and 1 set for testing. And then it's going to try to figure out the best thing. So if I instantiate this and run it, right? And then I say, okay, what are the values that I get from it? You'll see a whole bunch of stuff being printed out. But what we're really interested in is the stuff right at the end where it says the best values are alpha equal to 0.001 and binarize equal to 0.1. So now I can instantiate those as my actual Bernoulli knife base. I can fit it and I can predict it. So I'll run this quickly so you see the results out here. We get 7193, not a big change. But I also wanted to show you that I could change this verbose equal to 2. And then when I call fit, you'll see the 5-fold cross validation going on. So for 1 value of alpha and binarize, right, you'll see 5 runs happening, right? And then it changes out here again, and then it goes on, right? So again, out here, it's taking 4 of them as training and the last one as the testing, because we're not giving it the testing data set out here when we're doing the cross-fold, the 5-fold cross validation, all right? Okay, so I think I'm bang on time. I'm 2 minutes early. There was some other stuff I was doing with, taking the Fourier transform of that signal and trying to do clustering on that, but I'm skipping that for now. What I wanted to, quickly summarize is saying that if you want to start doing AI in your space, I highly recommend using Python. And what we've tried to show you in this session is a whistle-stop tour both of Python as well as the scikit-learn library. And this is, of course, not enough to get you started with writing your own code. But once I'll be sharing this notebook with the organizers. Once you have the notebook, feel free to use it as a starting point. Experiment with it, play around with it, and see how you interpret the results. What are the different options you can have, and so on. I've also created a separate notebook that gives you a little bit of a challenge, right? So you say, okay, what we did in KNN, for example, is just change the value of K. But the question is just, what are the different distance metrics that you can use? So this is very open-ended. You've actually got to go search, read up a little bit, and then put it in and see what the impact of this is going to be. And as a small starting point, when I create the KNN classifier, right, it says metric is Minkowski, right? So if you change the distance metric to something else, this is the parameter that you've got to change. Okay. The second is, again, we are assuming that all points. So if we have a 5 nearest neighbor classifier, we're looking for the 5 nearest neighbors, and then between them, we're saying who has the majority, right? But if you think about it, you could say that if something is closer to my test point, I want that value to have a greater weight than the one that is further away. So, what happens if you if you give it a weight? So now, again, this parameter's weights equal to uniform. So what would you change it to? How would you figure that out? Something like this. K nearest neighbor classifier question mark. You have weights, right? Default is uniform, possible values is uniform, distance, or something that you implement. Okay. This is slightly more complicated because what I've shown you is doing a decomposition using principal component analysis. There is another approach called TSNE, which supposedly gives better results. Try it out, right? So now instead of saying scikit-learn decomposition.pca, you'll have to replace this with whatever the equivalent call is for TSNE. So this is intended, so that you don't just try something random, but it's something very focused that you try to do. Okay. And then, this is just a little bit of NumPy exercise. So look at all of the normal abnormal signals, try to construct a signal that is most representative of all of them. So if you just take the pointwise value and take the mean and the standard deviation of each one of those, you'll look at a quote unquote representative normal distribution and abnormal distribution. And it might be interesting just to see what these look like. All right. So, so that was my whole, everything I wanted to talk about in this notebook and in general about how you could use Python and the scikit-learn library. I wanted to throw it open for questions from the audience. And, I would really, really appreciate feedback from you guys. Because I've made a lot of assumptions about the makeup of the audience, which may or may not be correct. But did this work? Was this useful? That kind of thing would be really appreciated. Right. So questions?
Yes, sir. Sir, we have few questions from the participants. The very first question is, how optimization plays an important role in machine learning?
So that's a very good question. So, and the reason I'm smiling is, okay, so first of all, here's my kind of distinction between AI and machine learning, right? So machine learning to me is very specifically neural networks, right? Yes. AI includes, of course, stuff that we did just now, principal component analysis. Well, not PCA, but K nearest neighbors, naive-based models, but also things like support vector machines, right? Or decision trees. Now, if you look at K nearest neighbors, there's not much optimization going on. We're just calculating distances and we are saying, okay, this is the nearest neighbor. If you look at, in the AI space, if you look like support vector machines, right? That's when you're actually doing, so the basic AI approach was something called a perceptron, which I think implemented a form of quadratic optimization, quadratic programming, right? Support vector machine also does that. And if you look at neural networks, basically what we end up doing is defining, when we're calculating weights for neurons, essentially what we are doing is we are defining a function as a convex model. And then we are finding the minimum of that convex function. How do you find the minimum of a convex function? Use gradient descent or stochastic gradient descent. So, what role does optimization play in machine learning? It's central. I mean, you can't do machine learning without optimization. And I actually think that we are ill-served by calling machine learning. It's not really machine learning, it's optimization, right? And people tend to get carried away by the oh, this is intelligence, artificial intelligence, and machine learning. And it's not. It's just under the covers. If you look deeply, it's basically optimization. It's basically linear algebra, right? Which is what we've been doing all of these years anyway, right? So, what role does it play? It is basically machine learning. Is how I would put it.
Yes, sir. Sir, the next question is, the data set actually matters on the accuracy. Then how to cross-validate the results?
Yeah, so if you look at what we did in this particular notebook, we took our data set and then we split it into a train and a test set, right? And then we use a test set to see whether what the accuracy of our results were. So that's one way of doing things, right? But in general, this is a function of, you've got to be careful about how you construct your experiment. So if we hadn't shuffled the data, and we just taken like the top 80% rows as our data set, then our test set would not have any normal data at all. It would all be abnormal data. And even a model that just closes its eyes and predicts something as abnormal would give us good results. In fact, it would be 100% correct, right? So when I was getting into computer science, my father used to joke that, his understanding of computers was GIGO, right? Garbage in, garbage out. So it's basically a function of the data that we have. If the data is good, then you have a good chance of being able to build good models and test them. If it's not, then it's not. Now, the problem with building models like this is they are relatively static in the sense that, you build a model and you have the results, but then what happens when you get new results? Right? That's when you typically want to not just stop with building a model once, but that's when you typically want to what should I call it? You want to keep retraining your model with new data as it comes in and improving with time, right? So how do we get a good test set? My hope is we just keep getting more and more data. And we keep retraining the models and updating our models to keep up with what we have.
Yes, sir. Thank you. Sir, there are various classifiers like KNN, SVM, AdaBoost. So which will be better for, is it like for different types of imaging data or whatever the signal data? The classifier may vary, like the performance I'm talking about.
Yeah, no, performance will absolutely vary. And which one is best just depends on what you're trying to do and the kind of data that you have. Right? That's kind of the long and short of it. So there's no universal guide to saying, for heartbeat data, use this, for MRI data, use that. And that's a nice thing about, if you look at Kaggle and what people have done, you have the data set, but people try a whole bunch of different approaches on the same data set. So some people will try like regular classifications, others will try decision trees, and still others will try neural networks, right? So it's just a function of the data that you have, and there's no uniform answer to that. One thing that I am extremely interested in is this whole notion of interpretability, model interpretability, right? And I'm not too much of a fan of neural networks simply because, at least so far, we don't understand why we are getting the predictions that we are getting. If you look at something like a k nearest neighbor, right, and we say, okay, why did this predict a 1 instead of a 0? You can look at it and say, okay, because these were the ones next to it. If you build like a linear regressor, right, you have an equation that says, y is equal to ax plus b. So if x increases by so much, y is going to change by so much. You can explain what's going on, right? We can't do that with neural networks. So which model to choose is not just in terms of accuracy, but it's also in terms of things like, if you want your model to be interpretable, then you need to choose the correct kind of the correct model that helps you with that. And there's a couple of other parameters, non technical, so non qualitative, or I'm sorry, non quantitative parameters that also impact which ones you want to be using. Right?
Yes, that means mathematical approach is very important whenever
Absolutely.
you're checking for the performance of any type of classifiers or whatever the machine learning
Yes.
experiment you're doing.
Yes.
Thank you very much, sir.
Yeah, I wanted to make a quick comment based on what you just said. I tell all of my students, especially undergrads, they get all excited with the minute they see data, they want to build a neural network and train it. Right. And I'm like, okay, hang on a second. You've got to understand what's going on out here. You can't just randomly put things into a box and shake it and see what comes out. So I call that mode of development monkey see, monkey do. So, they don't understand any of the underlying mathematics and they just do something. And if they get good results, everyone claps, right? But there's very little value in doing stuff like that. What you really should be doing is understanding the data, understanding the structure of the data, understanding what we want to achieve, whether it's classification or prediction or regression or whatever, and then choosing the right model because of our understanding of the data and what we want to achieve. Just randomly throwing things together is, I think, is I don't know. I don't like that approach at all.
Yes, sir. That is not the approach actually. That
Yeah.
is not required because you will be getting the result 96%, 100%, but you don't know what the data set is, whether
Exactly, it's meaningless.
all these things, all the mathematics, data set, and everything is going to matter a lot.
Yep.
Yes. Thanks a lot.
Okay.
Sir, we are now at the end of session.
Great.
So, on behalf of JSPM's Rajarshi Shahu College of Engineering, Department of ENTC, on day 2 of FDP on AI and Biomedical Engineering, I, Dr. Swati Bisikar, take this privilege to propose vote of thanks to distinguished and dynamic personality, Dr. Shrirang Karandikar, sir. Sir, you have given very informative session, interactive session, and with the demonstration hands-on, with actual real-time libraries, how it will work, scikit-learn, code description you have done, various databases you have told about the open source facilities available, everything. Thank you, sir. Thank you so much so that you have explored the various tools which are available in Python also, and not only Python, like whatever the databases like Kaggle and so forth. Thanks a lot. I'm sure that the participants will be benefited by your knowledge. Thank you, sir. And once again, I will thank you for sparing your valuable time with us. Thanks a lot, sir.
Thank you, and wishing you guys all the best for a fantastic FDP to come.
Yes, sir.
Yep.
Thanks.
Goodbye.
Have a good day, sir. Yeah. With this, we are now will be meeting at 2 p.m. for our post-lunch session. That will be session 3. It will be by Bhushan Garware, sir, from Persistent Limited. So